Hello again. We're going to get started in Chapter 3 here with Section 3.1. You'll probably notice in the title of 3.1, we're working with quadratic functions and models. So your success in Chapter 3 is dependent upon your skills in working with quadratic equations. So in Blackboard, I've posted a quadratic equation worksheet and 2 videos to go with that worksheet. Please watch the videos and work through those examples so you can get the necessary skills for success in Chapter 3. So now, assuming that you've done that review, you are ready to get into some quadratic functions. So we're going to look at the graphs of quadratic functions. We're going to look at writing quadratics in standard form, sketching sketching their graphs, and then working with the min or max of quadratic functions in real life applications. So let's look into a polynomial function, of which a quadratic function is a special type. So let's look at the definition of a polynomial function. It says, let n be a non-negative integer, and let a sub n minus 1, all the way down to a sub 0, be real numbers where a n is not equal 0. So look at this crazy function we have to represent a polynomial function. And actually, let me just give you a quick example of one so you can relate this definition to an actual example. Suppose I had f of x equal 4x cubed minus 2x squared plus 6xo minus 5. That is a polynomial function. And what you notice about polynomial functions is that these guys here are your coefficients on your variables. And in the definition, the an minus 1, and so on, that's just the way we can mathematically represent that we have coefficients in front of our variables. Now the x to the n minus 1, and so on represents your variable x, and that the degrees are going to be in descending powers. So if this is degree 3, the next one should be 3 minus 1, which would be a 2. And the next one would be 2 minus 1, which is power of 1. So we have our polynomials in descending powers, and this a0 at the end just means, hey, you have a constant. So this is just a real fancy way of describing polynomial functions in general terms. Now, we've already worked with polynomial functions because actually a line is a type of polynomial function, like 2x plus 1. The constant function is a type of polynomial function. The squaring function is a type of polynomial function, so you've worked with some of these before. We're going to specifically look at the squaring function, which is called a quadratic. So we're going to look at polynomial functions of degree 2, and the fancy name for those would be a quadratic function. So we're going to see many applications, such as the path of a projectile. If you were to throw something forward, that projectile goes up, but it eventually has to come back down, right? So the path of a projectile is a parabola shape, and quadratic functions will always graph as a parabola. So let's say I've got a projectile, its equation is a quadratic equation, a quadratic function. Or maybe if you look at a satellite dish, in your satellite dish, it opens, you've got some little receiver here in the middle. That shape is a type of parabola. Okay, so let's look at some of the theory of quadratic functions. So we may have one, that comes in, or I should say, the standard form of a quadratic function is ax squared plus bx plus c. A cannot be 0 because if a is 0, we wouldn't have that term and it wouldn't be quadratic. So we're going to have a second degree polynomial function, which is called a quadratic. Degree is 2. B and C can be 0, but A cannot. So here are just some quick examples of what a quadratic function might look like. We might have x squared plus 3. We might have, let's say, 3x squared minus 9x. We might just have 5x squared. Or we could have f of x equal x squared plus 6x plus 5. Notice the highest degree in all of these is 2. And so if I were to graph each of these, the graph would be a parabola. Now sometimes our parabolas open up and sometimes our parabolas will open down. And we're going to talk about some of the theory that goes with that. But just as a quick note, when you have quadratic functions, you must know the quadratic formula, which is a tool to help us solve quadratic equations. So just a quick note to have this guy here, the quadratic formula, which is used to solve quadratic equations, looks like this. Negative b plus or minus the square root of b squared minus 4ac, and that entire thing is divided by 2a. And where do the a's, b's, and c's come from? Well, they are the coefficients. So I basically ignore my x's and just pick up the coefficient a, the coefficient b, and the coefficient c. Take those three numbers, sprinkle them in these positions, simplify it, and that's how we use the quadratic formula to solve a quadratic equation. Keep this guy handy. He'll come in where we'll need to use him to solve some quadratic functions. Maybe not in this section, but further on, later on. Okay, so if I have a quadratic function, the graph will always be a parabola. So if I've got ax squared plus bx plus c, if that first coefficient a is greater than 0, all that means it's positive. If the front coefficient, or the coefficient on x squared, is positive, your parabola will always open up. If that coefficient is negative, then your parabola will open down. Always, always. When your parabola opens up on this side, that vertex right there is going to be a minimum. So when a parabola opens up, the vertex is always a minimum. When a parabola opens down, that vertex is always a maximum because it's the highest point on that parabola. It's a minimum here because it's the lowest point on that parabola. The vertex, we refer to it as the ordered pair. It's always going to be an ordered pair, and we just call it h comma k. H comma k. There's our vertex. So we'll just give it a name, h comma k. Now, your axis of symmetry, which means the line that if you fold your parabola across and it overlaps itself, that's called the line of symmetry, and it always occurs at the x value of your vertex. Or in this case, we're calling it h. So this is our axis of symmetry. That dotted line is our axis of symmetry, and it always occurs at x equal h. The first coordinate in your vertex. X equal h. That is your axis of symmetry. That's the line that if you fold your parabola around it, it will cross over itself. It will match the mirror image of it. So our quadratics will actually come in two forms, mostly. We'll see it in this standard form here at the top, or maybe this standard form here at the bottom. They graph out to be parabolas, but when it's in this form, it makes it a little bit easier to find some information. So when it's in this form, I would look at the coefficient a in front, and if a is a number greater than 0, it'll open up. If that a is a number less than 0, it will open down. Also in this form, a very easy item to grasp is the vertex. The vertex comes from the h and the k. Remember back in chapter 2? Remember when we had a number inside the parentheses that told me to go left or right? And the number outside the parentheses told me to go up or down. So all I need to do is pick up the value of h, pick up the value of k, and I have got my vertex, which is an important part of my parabola. Now to find x and y intercepts, we will let's just concentrate on x-intercepts first. To find the x-intercepts, I set my equation equal to 0. And remember, another name for an x-intercept would be the zeros of my polynomial function. So I just set my equation equal to 0 to find my x-intercepts. To find my y-intercept, I plug a 0 everywhere I have an x. Then I'm going to plot the intercepts and my vertex and maybe some other points to get the shape of my parabola. So I think I'll stop this video here. This will be our introduction to quadratic functions, and then what we'll do is apply what we've talked about so far to graphing some problems in the next video. If you ever have any questions, you know you can just email me and let me know.